chapter 9. This is the last chapter of the semester. Okay, so chapter 9. This is the last chapter of the semester. It's going to be considered systems of differential equations. Okay, so systems of differential equations. Right, so it's going to consider the systems of differential. So what is a system of differential equation? Let me first show you such an example, which I'm going to call it the spring mass system. Okay, so here is we have a spring mass system on the horizontal axis. Okay, so we have a spring mass system on the horizontal axis, right? So you have a spring mass system on the horizontal axis where the floor has no friction, right? So let's say the first spring, okay, so this is the first mass, then there's a middle spring, and then there's another mass, M2, there's a third spring that's like this here. Okay, so the first spring has a Hooke's constant K1, second spring Hooke's constant K2, and third spring it has a Hooke's constant K3, right? So Hooke's constant K3. Now I want you to have a differential equation that can describe the motion of both M1 and M2. Can you do that? Well, how are you going to do it? Well, you're going to just assume, okay, so you're going to just assume that the first mass is moved by x1, the second mass is moved by x2. You want to analyze the acceleration, right? So remember, I'm using the fact that ma is equal to f, where a is what we call the acceleration. Right, so we're going to use the ma equals to f, where a is going to be called the acceleration. Okay, so the a is going to be called the acceleration. Okay, so now as long as you have this, okay, so as long as you have this, when you have the acceleration, so let me assume that the first mass moves by x1 and the second mass moves by x2. Is that going to everybody? Okay, so if you first mass moves by x1, second mass moves by x2, what is the force acting on the first mass? Suppose there are external forcing. There's first external forcing F1, the second external forcing on F2 acting on the mass. But what about the resistance forces in the spring? Well, you have to have the first mass moves by x1. So that means the first mass. Okay, so the first mass is going to be moved by x1. So it is here the first mass. So the first spring is going to be elongated by x1. Is that good, right? So there's a motion in x1 for the first mass, and the second mass is moved by x2, right? So the second mass is going to be moved by x2, right? So that means with respect to the initial position of the second mass moved by x2, which means the K3 must be contracted by another quantity x2, right? So with respect to its natural length. The only problem is that what happens to the middle spring? Is that good, right? So what happens to the K2? Well, the K2, you can see that on the first way, with respect to the initial positions, the left end of K2 moves to the right by x1, but the right end of K2 moves to the right by x2. Is that good, so the K2 is going to be deformed by an aggregate fact of both x1 and x2, because both of them are moving to the right. Is that good, right? So both of them are moving to the right. So that if the K2 is x1 is moved to the right, then the K2 will be contracted. If it is contracted, it is going to give, okay, so it is going to give the M1 a resistance force in this direction. But if K2, the right end of K2 is extracted by x2, then it is going to be it's going to be straightening, so that it will give a force to this way. So that's this is the K2 of x1. This is the K2 of x2 acting on the M1 mass. Is that good, right? So if you take the positive direction to be this direction, then you're going to see that M1 d square of x1 divided by dt square. This is nothing but the acceleration. Okay, so this is nothing but the acceleration of the first spring of the first mass is equal to the forcing. But the forcing is going to be, so what does K1 do? Well, K1 is going to be elongated. So it's going to give you a force, which is K1 x1 in a minus sign. So minus K1 x1. But the K2 is kind of a little bit complicated. It is going to give the mass a minus K2x1, but then a plus of K2x2. Is that good, right? So because of both the M1 and M2 are deformed, right? So, and maybe plus the first external forcing F1 of T. So that's kind of what happens to the first mass, right? So that's what happens to the first mass. And you can sort of see that the second mass has a similar stuff. So d square x2 dt square, the second mass is the same thing. So the K2 is being contracted. It means that it will resist a force which is of the magnitude K3x2 to the left. So minus K3 of x2. But for the middle force, it will be different, because if you kind of elongate the K2, then the K2 is going to drag you back so that's kind of minus the K2 of x2. And then you're going to have a K1 also, because if you push the K2 to shorten it by x1, the K2 is going to give you resistance force in both directions, both here K2x1 and K2x1 here. So that's plus a K2x1 and plus the second force F2 of T. Is that good, right? So somehow after this very classical, very standard mechanical, so that mechanical analysis, right? So the mechanical analysis, you end up with this system of differential equations, which simply says, okay, so you end up with this differential equation, which simply says M1 x1 double dot is a minus of, okay, so K1 plus K2 multiplied by x1 plus K2 multiplied by x2 plus the first external forcing. And the second one is M2 x2 double dot is a minus of K3 of x2, right? So K3, okay, so K3 plus K2. So let me write it in a better way. Okay, so let me write it in a better way. So let me use, okay, so let me use, okay, so let me use K2 of x1 minus, okay, so K2, okay, K3, yeah, K3, K2, okay, so K2 plus K3 of x2 plus the second external force F2 of T. Is a good family, right? So you have such a very nice system of differential equation. Now, why do I call it a system of differential equation? It is because are you able, here I have no friction, okay, so no damping. Are you able to solve this, let's say, the first equation? Are you able to solve this equation without the second equation? It is not possible, right? Why is that the case? Because you don't know x2. You know, if you know x2, you can do it. But if you don't know x2, it is an equation x1 which involves an unknown variable x2. Is a good family. So that's not a good idea. And for the x2 equation, same thing. So it's a differential equation for x2, but involves x1. So these two equations are somehow coupled. These two equations are coupled together, so that in order to solve the first equation, you have to solve the second equation. In order to solve the second equation, you have to solve the first equation. Is a good family. Okay, so this kind of coupling system, okay, so this kind of coupling system is going to be called a system of differential equations. Okay, so this kind of coupling system is going to be called a system of differential. So this is going to be very popular. Okay, so for this chapter, okay, so we're going to call it the system of ordinary differential equations. Okay, so we're going to call it the system of ordinary. Here I want to show you another example, which probably, okay, so which very probably, okay, very probably you will see this example by your final exam. Okay, so this is very likely to happen on your final exam. Okay, so I would like to emphasize this kind of problem again and again. Okay, so very likely it's going to happen on your final exam. So what happens to this problem is saying that you consider two tanks. They hold initially 100 gallons of pure water for each. A mixture of salt and water at a concentration of 4 ounces per gallon flows into tank 1 at a rate of 5 gallons per. So you're very familiar with this type of question, tank problem, right? So, but here we have two tanks. Okay, so the well-stirred mixture is going in tank 1 is going to drain into the environment at the rate of 3 gallons per minute, and from tank 1 to tank 2 at the rate of 2 gallons per minute. Another mixture of salt and water at a concentration of 5 ounces per gallon flows into tank 2 at a rate of 2 gallons per minute. well-stirred mixture in tank 2 drains into the environment at the rate of 2 gallons per minute. If Q1T and Q2T denote the salt content in ounces in tank 1 and 2, respectively, can you solve set up but do not solve the differential equation, initial conditions that models the flow process? So what happened here, the problem looks very long, right? So the problem looks very long, but a good idea is to draw pictures, right? So the tank problem has, of course, there's a tank 1, and there's also a tank 2, right? So there's, these are the two tanks. So what the problem say? Well, the problem says that initially, these two tanks hold in 100 gallons of pure water for each, right? So 100 gallons of pure water for each. So initially, that 100 gallons of pure water for each tank, right? So for each tank. Now when you draw pictures, you should put data there in order to make it more visible, right? So a mixture of salt and water, concentration of 4 ounces per gallon, with a rate of 5 gallons per minute, right? So that means this is going to enter here is 5 gallons per minute, is 4 ounces per gallon, right? 4 ounces per gallon. This is a mixture of salt, right? So mixture of salt and water that's going to enter the tank, right? So, and a well-stirred mixture drains into the environment at the rate of 3 gallons per minute, right? So well-stirred mixture drains into the environment at a rate of 3 gallons per minute. That's well-stirred mixture. And it also drains, right? So it also drains from tank 1 to tank 2 at a rate of 2 gallons per minute, right? So from tank 1 to tank 2, it will be at a rate of 2 gallons per minute. Is that good, family, right? So, and then you look at more conditions. It says that another mixture of salt and water, concentration of 5 ounces per gallon, flows in tank 2 at a rate of 2 gallons per minute, right? So that means you have another source, right? So that's 2 gallons per minute is 5 ounces per gallon and flows into tank 2. And once you have this tank 2, you are going to see that flows in 2 gallons per minute, right? So it rates, okay, so concentration of 5 at the rate of 2. Well-stirred mixture, it drains into the environment at the rate of 2 gallons per minute. So well-stirred mixture drains into the environment at the rate of 2 gallons per minute. Is that good for everybody? Okay, so these are all the conditions that are provided, right? So all the conditions that are provided for this problem. Now the question is to ask you, can you solve and can you set up a differential equation Q1T and Q2T? They denote the amount of salt in tank 1 and tank 2. So Q1T and Q2T denote the amount of salt in tank 1 and tank 2. How do you model a differential equation? So that kind of looks very complicated because previously in our previous lectures, we are going to have just one tank with this kind of salt and concentration problem, right? So that's just one tank. But now, unfortunately, it becomes 2 tanks. So, but if you look at the problem carefully, you will realize that it is not that hard to solve as it appears, right? So it's not that hard to solve as it appears. So what's the basic principle? Okay, so what's the basic principle in attacking this type of problems? Well, the basic principle says that the per net rate change of the amount of salt is the inflow fluid rate multiplied by the inflow concentration minus the outflow fluid rate multiplied by the outflow concentration. Is that good? Okay, so that means you have to analyze, right? So the dq, no matter which tank it is the inflow. Okay, so it's the inflow minus the outflow. But once you consider the inflow and outflow, you have to realize that this is the inflow of the salt. So that's the inflow fluid, right? So inflow fluid multiplied by the concentration is the inflow of salt minus the outflow, right? So outflow fluid multiplied by the concentration. That's it. Is that good, right? So you have to analyze the inflow fluid and concentration. So if you want to look at Q1, right? So dQ1 over dt, you can use this principle. What's the inflow fluid? Well, the inflow is 5 gallons, right? So the 5 gallons multiplied by the inflow concentration is 4 ounces per gallon. Is that good, family? What about outflow? There are 2 outflows. There is a 3 gallons and 2 gallons. So that's kind of a 5 gallons outflow, right? So 3 plus 2, right? So 5 is 3 plus 2, right? So, but what's the outflow concentration? Remember, this is a well-studied mixture, so that means you have to use Q1 divided by the volume. What's the volume? Well, the inflow volume is 5, outflow volume is 5, so it will never change. So that's over 100. This is just your Q1. Is that good for everybody? Right? So this is a very simple differential equation that models the amount Q1. But if you do Q2, then you're going to have similar principles. The dQ2 has an inflow fluid. The inflow fluid has two sources, which is here and here. Is that good for everybody? Right? So the 2 gallons per minute is the inflow fluid rate multiplied by the concentration is Q1 divided by 100. That's the concentration. And you also have an inflow 2 multiplied by 5 ounces per gallon. That's a 5. That's another inflow fluid. And what about the outflow? Well, the outflow is 2 multiplied by the concentration. The concentration is now Q2, right? So Q2 divided by the volume. But what's the volume? Well, initial volume was 100. Per minute, you have 2 plus 2 is 4 minus 2. So that's plus 2T, which is the volume. Is that good, right? So if you put these two equations together, you're going to see that, well, you may be able to solve Q1 independently, but in order to solve Q2, you have to solve for Q1 first. Is that good for everybody? Okay, so that's a kind of very important phenomenon, which is going to call it the differential equations with a discontinuous right hand, the differential equations, this kind of very important phenomenon is going to be called differential equations, systems of differential equations. So that means that the differential equations are kind of coupled, right? So you have a coupling of these differential equations. They're going to form a system of what we call it a system of differential equations. Okay, so that's what we're going to say, a system. Okay, so the system of differential equations. Right, so system of different. So what's the general form of a system of differential equation? So here, the modeling. Okay, so the modeling by systems of differential equation might be a very important part for your, especially for your final exam. Okay, so especially for your final exam. Okay, so here I have listed many relevant exercises for you to practice. And you can see that most of them are double tank problems, right? So most of them are double tank problems, but very occasionally they also test the coupled vibration, which means that you have two oscillators, they are kind of vibrating, right? So with the first example we talked about in today's lecture. Okay, so here, let me finish today's lecture. Okay, so let me finish today's lecture by talking about the system of first order equations, right? So if you want a very abstract form, right? So that's first order, right? So that's a first order system of differential equation. Then you can write it in this way, right? So x1 dot is equal to the first function, maybe t, x1, x2, up to the n, xn. And you have x2 dot is equal to the second function of t, x1, x2, up to xn. And you continue here. So the xn dot is equal to the nth function t, x1, x2, up to xn. So these f1, f2, and fn's are enveloping functions, right? So that means that in an abstract way, you're going to put a relation between x1, x2, up to xn in this relation, okay, in this relation. However, the point here is that you can see the only derivatives that appear are first order there. That's why we say is this a system of differential equations plus first order, right? So system of first order differential equation. I mean, sometimes, for example, we've been talking about system of the higher order equation. Let's say here, this is not a system of first order equation. This is a system of second order equations, right? So, but in our note, here we're going to define only the system of first order equations. Okay, so system of first order equation. Now, if you have a system of first order equation, you want to find a particular solution, you also need the initial conditions. Let me say x1 of 0, x2 of 0, up to xn of 0 are the initial conditions that are going to be given to you. Okay, so xn of 0. And these are the initial conditions. Okay, so that's about the system of differential equations in the abstract example. Okay, so let me stop here for today's lecture. Let me come. So last lecture we had been starting to talk about the systems of differential equations, right? So the systems. Okay, so systems of ODEs, right? So we have seen that a system of ODE is like a system of this. Let me see. Okay, so it's like a system of ODEs where you have so we've been talking about this in our last lecture, right? So that's has been talked about in our last lecture. Okay, so what happened here? Is that there are some examples like the modeling problems that you have to be familiar with. Okay, so you have to be familiar with in regards to the modeling by differential equations. Okay, so it can be either a double tank problem. It can be either a double tank problem, or it can be a coupled vibration problem. Those type of problems have been talked about in our last lecture, right? So in our last lecture, I talked about both types of problems. Okay, so both types of problems. Okay, so now what's the general system of equations look like? Okay, so a general. Okay, so let's say a general. Okay, so general system of ODEs, right? So what's the general system of ODEs can look like, right? So well, a general system of ODEs as it was shown here. Okay, so as it was shown here, it has the form. Okay, so it has the form of x1 dot is equal to f1 of t x1 x2 up to xn, and x2 dot is equal to f2 of t x1 x2 up to xn, right? So and then it's until xn dot is equal to fn t x1 x2 up to xn, right? So that's the system of ODEs. That's first order, right? So that's a system of ODEs. That's like a first order system of ODEs. Okay, so why are we interested in considering only the first order ODEs? Well, we consider first order ODEs because the initial conditions x1 0. Okay, so x1 0, x2 of 0. Okay, so is x2 0. Okay, so and xn of 0 is xn of 0, right? So that's the systems of first order ODEs. Okay, so this is a system of first order ODEs. Okay, so this is a system of first order ODE. Now the question here. Okay, so the question here is to ask. Okay, so is to ask. Why do you like to consider, right? So systems of first order ODEs, right? So it is natural to see. It is natural to see that we have also systems of high order equations, right? So we also have systems of high order. For example, when we were talking about the spring mass systems, this is a system of second order equations, right? So that's a system of second order equations. So why don't you consider systems of high order differential equation, but only considering system of first order differential equations, right? So that's the question. So however, it is interesting to see. Okay, so it is interesting necessary to see. Okay, so necessary to see that the first order the system of ODEs have initial conditions like first order equations, right? So all these initial conditions only consider the zeros derivative, the initial values, right? So that's important. So let me now explain why we want to consider first order ODEs instead of high order ODEs, right? So now let me, in order to explain this, let me show you an example. Okay, so an example here says that if we have the vibration equation, this is the vibration equation. Can you write it in the system of first order differential equation? So the vibration equation, okay, so right, so the vibration equation, as we have seen before, has the form mu double dot plus, okay, so plus gamma of u dot plus k of u is equal to the external forcing, right? So that's the vibration equation. Can you tell me what is M? Anybody has idea? Anybody can tell me what is M? M? Any idea? Anybody has idea? You can speak loudly if you want. Anyone has idea?
Mass.
M is the mass, right? So thank you very much. Yes, so that's good. M is the mass. What is gamma? Anybody has idea? Gamma? Anyone has idea? What's the gamma?
Dampening constant.
Yeah, that's very good. Okay, so thank you very much. This is a damping constant, right? So damping constant. What about K? K is equal to, any idea? K. Anybody has idea? Like what's K?
Spring constant.
Spring constant, right? So very good. Okay, so very good. Okay, spring constant, or sometimes we call it the Hooke's constant, right? So Hooke's constant, right? So this is kind of very important. Remember, here today we are today now it's April the 15th. Okay, so we have about 2 to 3 weeks to finish all the lectures, right? So we're very close to the end of the semester. So you have to start. Gradually review what has been there in the lectures, right? So a good thing for this semester is that in part 2 of the semester, all the lectures are now can be you can view the videos on the cameras. So that will hopefully will help you. Okay, so that hopefully will help you to go through the materials for this class. Okay, so for this class, so that's kind of the thing about the vibration equation. Now the point here is that I would like to rewrite the vibration equation into a system of differential equations. So what should I do? Any idea? Well, the idea. Okay, so the idea here is the following. So I'm going to let u dot is equal to v. Is that good, family? Okay, so I'm going to let u dot to be equal to v. Now let me ask, if u dot is equal to v, then what is the v dot? Any idea? The v dot, because u dot is v, so v dot must be u double dot. Is a good family, right? So, but this equation simply tells you that you can calculate u double dot as the external forcing, right? So external forcing minus gamma of u dot minus k of u divided by the mass. That's u double dot. Is a good family. So therefore, this one is nothing but the external forcing minus gamma of u dot minus k of u divided by the mass. So if you write it in this way, you're going to see that this is minus gamma over m of u dot minus k over m of u plus external forcing divided by m. So that's kind of natural way to write v dot. But what is u dot? If u dot is equal to v, what is the u dot here? Well, the u dot here must be equal to v. Is that good, family? So therefore, you end up with such a system saying that u dot is equal to v and v dot is equal to minus k over m multiplied by u minus gamma over m multiplied by v plus the external forcing divided by m. Is that good, family? Right? So this is how you turn. Okay, so this is how you turn a second order equation into first order equations. Right? So that's very simple. So you just let the derivative, you have the second order derivative is the highest derivative. You just let the first order derivative to be another quantity that you would like to calculate. And you take a derivative of that quantity. It must be second order derivative. Therefore, you came up with such a system of first order differential equation. So this is a very nice, very important idea. It tells you that it is possible to turn any higher order differential equation into first order equation. You really don't need higher order differential equation, but you only need first order equation because you are able to turn any higher order differential equation into first order equation via such a method. Is a good family. Okay, so what happens if the question has initial condition? Remember, previously our initial condition was were mainly like u0 and u prime 0 is v0, something like this. So if that is the case, then the initial conditions, right? So initial conditions initial conditions should only take the form u of 0 is u0 and v of 0 is v0. So that's the initial conditions you would like to take for the system of first order equation. So that's still the case. So you're able to turn both the differential equation and the initial conditions into a system of first order equations, right? So that's kind of the same. You're able to turn your differential equation, both the differential equation and the initial conditions into a system of first order equation. So this is a very nice idea. Okay, so this is a very nice idea. Now the question is to ask the in reverse direction, right? So in a reverse direction, suppose you have a system of first order equation. Are you able to reduce their derivatives? Okay, so are you able to reduce their derivatives and write it into a system of higher order differential equation, right? So that's kind of a reverse type of question. Okay, so that's kind of a reverse type of question that might be of interest, right? So that's kind of reverse type of question that might be of interest. And this is actually indeed the case. Okay, so this is actually indeed the case. For example, here there's an example saying that you have a system of first order equations. Okay, so x1 dot is equal to, so that's a system of first order equation x1 plus 2x2. Okay, so x1 plus 2x2, and then you have the x2 dot, right? So the x2 dot minus x1 minus 3x2. Okay, so you're going to have x2 dot. Okay, so it's minus x1 minus 3 times x2, right? So you have both these two equations. Now I want to write it into a second order system of differential equation. So I want to write in a second order system of differential equation. What should I do? Well, you can kind of take one more derivative. So let's say x2 double dot is equal to minus x1 dot minus x2 dot, right? So, but what's the x1 dot? Well, x1 dot is equal to x1 dot is equal to what? Well, it's equal to minus x1 minus 2 times x2 minus 3 times x2 prime. Is a good favorite. So the only thing left is you don't know this x1, but it doesn't matter. You can calculate this x1, right? So you can calculate this x1 from here, right? So you can calculate this x1. So maybe I change it. I will do it in another way, right? So that I will do it in the other way around. Okay, so if I do it in the other way around, right? So I will start from x1, right? So I will start from x1. So what happened here is that let me start from x1. So x1 double dot is equal to x1 dot plus 2 times x2 dot. Is that good, right? So that's kind of the same. But the x1 is now equal to, so the x1 is actually equal to x2 prime plus 3 times x2 minus, so x2, so minus x2 prime, okay, so minus 3 times x2, because you can move this one to the left of this equation, you move this one to the right, you get this. So that means x1 prime is minus x2 double prime minus 3x2 prime. So that's x1 prime. So once you have this, that's minus x2 double prime minus 3x2 prime. Okay, so that's x1 prime plus 2 times x2 prime. So you actually get the relation between so that's x1 double prime, right? So that's maybe I should so that's, I'm sorry about this. So let's I should start with x2. Okay, so I should start with x2 prime. Sorry, just let me just look at what we have here. Okay, so what happened here is that first of all, x1 prime is equal to x1 plus 2 times x2. So it calculates x2 in terms of x1, right? So once you calculate x2 in terms of x1, you take a derivative of x2. So that's x2 is equal to prime is this this one, right? But x1 double prime. Okay, so x1 double prime minus x1 divided by 2. But x2 prime. Okay, so x2 prime you can calculate it from this equation. Okay, so that means if you put everything together, it means that this left-hand side is equal to this side. So you get this equation like this, right? So the equation like this. But then you're able to calculate the x2. Okay, so you're able to calculate this x2 via x1 prime minus x1. So that's this from here. Okay, so because x2 is calculated from x1, so in the end you get an equation for x1. Okay, so precisely the idea that I had there. Okay, so the idea that I had there is to kind of make use of both these equations, right? So what happens there is that you're going to start from x2 prime, right? So x2 prime, so that x2 double prime is minus x1 prime minus 3x2 prime, right? So but x1, x2 prime can be calculated from what you have there, right? So that's x2 prime is already known. So x2 prime, okay, so but this x2 prime, right? So x2 prime is minus x1 minus 3 times x2, right? So minus 3 times x2, but it is also equal, right? It is also equal to this x1 prime minus x1 divided by 2. You take a derivative, so that's x1 double prime minus x1 prime divided by 2. So in the end, you get an equation. X1 double prime is equal to minus 2 of x1 minus 6 of x2 and plus x1 prime, right? So and then you just need to recalculate the x2 in terms of x1. So that's kind of not hard to do. So minus 6 times x2 is x1 prime minus x1, right? Divided by 2 and plus x1 prime. So in the end, this is minus 2 times x1 minus 3 times x1 prime minus x1 plus x1 prime. So this is actually 3. So x1, okay, so minus 2 times x1 prime. So that's kind of an equation for x1 that you finally obtained. Okay, so these two examples shows that higher order. Okay, so it shows that higher order differential diffie. All right, so and the first order systems. Okay, so first order. Okay, so first order systems of diffie, right? So these two things are interrelated, right? So a higher order differential equation can be turned into a first order system of differential equation, and vice versa. If you have a first order system of differential equation, you can always turn it back into higher order differential equation. So this is kind of a nice idea, right? So this is kind of a nice idea. So what's the general version of this idea? What's the general version? The general version looks like this. Okay, so the general version of this idea looks like this, right? So the general version looks like this. So if you have a higher order equation, you might write it as xn double derivative, right? So it's equal to f, right? So it is equal to the capital F. Okay, so let me use y as my variable in order to comply with the lecture notes. Okay, so let me use y, and then I will use the x as new variables. So that's f of t of y derivative up to yn minus 1's derivative, right? So that's a very general high order equation. How are you going to turn it into first order diffie? Well, you can turn it by this idea. So x, let's say x1 is equal to y, right? So x1 is equal to y, x2 is equal to y prime, x3 is equal to y double prime, dot, dot, dot. So here you see you must end up with y, which derivative? So you only need to add n minus 1. Remember, if n is equal to 2, you just need one variable. So that's x of n, n is equal to y n minus 1. Why is x of n? Because you started from the zeroth derivative. Is that good, right? So which is just 1. Okay, so therefore you're going to have a system of equation. x1 dot is x2 because y prime is y prime. So x1 dot is x2, x2 dot is equal to x3. So that's consecutively, right? So until you get xn minus 1 prime is equal to xn, right? So xn minus 1 prime. But then you get xn prime. What is xn prime? Xn prime is like yn. But what is yn? It's f of t y prime according to this definition, right? So of this equation. But these y's are already defined. So they are x t of x1, x2 up to xn minus 1. And is that good, right? So xn is equal to yn minus 1. So this is the whole differential equation, right? So the whole differential equation in a clear way. Okay, so in a clear way, it should be written so we can ignore this, right? So we don't need this, right? So we can simply write everything, right? So we can simply write everything as xn derivative. Okay, so we can simply write everything as xn derivative is f of t x1 up to xn. It's a good family, right? So that's kind of helps us to turn a higher order equation into a system of first order equation. It helps us to turn a higher order equation into a system of first order equations, right? So that's kind of, let me use the prime here. Okay, so let me use the prime here. Okay, so I will not use the dot, I use the prime. Okay, so that's kind of turns this equation into a system of first order equations, right? So that's kind of the thing that we would like you to do, right? So you're always able to turn this higher order equation into a system of first order equation. And this is very important. Okay, so this is very important, and it might occur in some of your final exam questions. Okay, so I can tell you it might occur in some of your upcoming exams and final exam questions. Okay, so for example, here I have listed you like two more examples that are related to this issue. Okay, so there's two more examples that are related to this issue. Okay, so it shows you that if you have a differential equation, I would like you to turn it into systems of first order equations. These are high order differential equations, and you're asked to turn them into systems of first order differential equations. Please take a look at these two examples, as they might help you to prepare the next exam. It won't occur today, but it might help you to prepare for the next exam. Okay, so that's all I want to have for this one. Okay, so now I have several. So now you can see. Okay, so now you can see that once we introduce the system of differential equation, as long as we introduce the system of differential equation, the solution theory for differential equations. Okay, so the solution theory for differential equation suffices, right? So suffices to solve. Okay, it suffices to solve differential equations, which is a first order system, right? So you don't have to be worried about any high order differential equation. You only have to solve first order system of differential equation. So the question here, okay, so the question, right? So question for the remaining part of the semester is how do we solve, right? So how do we solve systems of first order equations? Right, so how are we going to solve the system of first order equation? Is there any particular method that can help you to solve the system of first order equations? Well, the idea is kind of very simple. Okay, so the idea is kind of very simple. So we can see that system of first order equations in general should take a form x1 dot is equal to f1 of t x1 up to xn, and x2 dot is equal to f2 of t x1 up to xn, and etc. So xn dot is equal to fn of t x1 up to xn. So this is a system of first order equations, right? So now how are we going to solve it? Well, the simplest way is to solve system of first order and the linear equations. By system of first order and the linear equations, it means that it is even simpler. So remember, what is our linear equation talking about? Linear equation previously, it's like a linear combination. So that's what happened here is that there must be a11 of x1, a12 of x2, plus dot dot dot, plus a1n of xn, and etc. So x2 dot is a21 of x1 plus a22 of x2 plus dot 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 plus a2n of xn, etc. Right? So xn dot is equal to an1 of x1 plus an2 of x2 plus dot 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 plus ann of xn. Right? So that's kind of the system of first order equations like this. Right? System of first order equations like this. Right? So this is a kind of simplest type of system of equations that we call it linear equations, right? So remember, in our linear equations, there are also like right-hand side, right? So the G1, G2, these are like the non-homogeneous equations. Is that good, right? You have the homogeneous difference between the homogeneous and non-homogeneous equations, right? So that's kind of the general thing. So that's first order systems of linear equation. Now, in regards to this equation, there is actually a theory. Okay, so there is actually a theory. It says that if the a's, okay, so if these a's are functions of t, right? So let's remember, in general, the system of linear equation is like an of t, right? So plus dot 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 plus a0 of t of y is equal to g of t. That's what we have been talking about before. That's a linear equation, right? So that's linear. So this is like a system of linear equation where these a's might be functions of t. And therefore, we can bring in a very simple theorem that we have learned before. The theorem says that if you have a first order system of linear equation, then as long as the coefficients, right? So first of all, this equation is in a so-called standard form. We have emphasized the standard form many times in our lectures. Is that good? But this is an equation in standard form. Okay, so this is an equation in standard form. So equation in standard form, therefore it tells us that if all the coefficients for the equation in standard form are continuous functions, right? So if they are continuous function, then you are going to have a unique solution, right? So that's what we have learned before. If all the coefficients Pij are continuous, then you are guaranteed to have a unique solution for the system, right? So somehow you can see that if we want to solve a system of first order equations, then you start from system of first order linear equation. This is exactly what we have been doing before. Before we were just considering one equation. We consider one higher order differential equation. We don't know how to solve it. Then you should consider the higher order linear equation. And in particular, you start from the higher order second order linear equation. We have the theory about the Wronskian, right? So the linearly dependent solutions, fundamental solutions, homogeneous and non-homogeneous problems. You have to find particular solution, right? So general solution, particular solution, method of undetermined coefficients, method of variation of parameters, right? All this information were discussed in our previous lectures. And I would like you to start to gradually review these notions because the final exam is upcoming. Okay, so although the semester has been broken by the pandemic, it doesn't mean there's no exam finally. There will be a final exam which covers all this material. Of course, we're going to do reviews for this final exam. So that's kind of the idea. So you would like to solve a system of first order equations. So that means if you want to consider first order equation, it has the form x1 dot, right? So is equal to, let's say x1 dot is equal to the p11 of t of x1 plus dot 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 plus p1n of t of xn, right? So plus g1 of t. And similar thing, x2 dot is p21 of t of x1 plus dot 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 plus p2n of t of xn plus g2 of t, and etc. So in the end, xn dot is pn1 of t of x1 plus dot dot plus pnn of t of xn plus gn of t. So that's kind of a system. And what about the initial condition? You want x1 0, x2 0, right? So this is x1 of 0, x2 of 0 dot dot dot, xn of 0 is equal to xn of 0. So that's kind of, you have to put all the initial conditions there. Okay, so that's how the problem. So the problem is to how do we solve the system of first order equations that looks like something like this, right? So how do we solve the system of first order equation that takes such a form, right? So that takes, so it looks very complicated, right? So, but how are we going to solve it? Well, the idea of solving this system of first order equation is to consider a vector, right? So that, let's say the vector x of t is equal to x1 up to xn. So this is a column vector. Then you have to set another matrix. P of t is what we call the coefficient matrix. P11 of t up to P1n of t, right? So P21 of t up to P2n of t, right? So dot Pn1 of t up to Pnn of t is a good family. And I'm going to set a vector, another vector g of t is the right hand side g1 of t, g2 of t, right? So up to gn of t. So that's a vector. So if you are familiar with matrix vector notation, you can see that this vector, right? So this vector, and this is a vector, right? So, and this is the derivative of the x vector, but this vector is nothing but the matrix P of t multiplied by x of t, right? So this is kind of a matrix vector notation, right? So remember, the matrix vector notation is just the same that if you have P11, let's say P11, P12, P21, P22, it's going to be multiplied x1 and x2. What you're going to say is that you just multiply this with this, sum together, P11 x1 plus P12 x2, and for the second term, the same thing. So you're going to recover this whole vector. Is a good family, right? So if you do that, the whole equation becomes x dot is equal to, right? So this matrix vector notation plus the g dot plus the g of t, which is a vector. So that's the end. In the end, you'll consider an equation x dot is equal to p of t multiplied by x plus the g of t. So that's kind of the relation between matrix vector notation. Now, if you look at this equation, it looks very much like x dot is equal to pt of x plus q of t. Did you remember how do we solve this equation? We solved this equation via, can anybody tell me the method? Just to check you're still on the other end of the internet. Anybody has an idea? How do you solve this first order equation like this? Can you tell me? Any idea? How do you solve the first order equation like this? Anybody has an idea? There is a name. What factor? Which factor? Anybody has an idea? Are you still there? You're lost or you're still there?
Integrating factor.
Integrating factor, right? So very good. Okay, so I like it. Okay, so integrating factor. Okay, so just to double check, you're still on the other end of the internet. Okay, so integrating factor method. And what is the integrating factor? Integrating factor says mu of t is e to the power of this pt dt. Remember, this equation is already in the standard form. We talked about it, emphasized it before, right? So that's the integrating factor. So that means if you kind of write, if you look at this equation, it looks like impossible to solve it. It's kind of too many equations there. But if you abbreviate it, right, introduce these notions like x, p, and g, you're able to write this everything like very much like what you have learned before. It's just you need an integrating factor like mu of t, maybe it's e power of the matrix pt dt. But this is like an absurd analogy, because if you just this is easy to understand. You consider the function, integrate it, raise it to an exponential. But what does it mean? You have a matrix, you integrate it, raise it to an exponential. It's not clear at all what this is. It's a good family, right? So it's an analogy, but this analogy is only analogy. Schematically, it's an analogy. It doesn't contain any information there. It's a good family, right? So that's kind of the thing. So that means we have to really make sure that we understand these matrices, right? So we have to make sure that we understand these matrices and the vectors. Is a good family. Okay, so mathematics of matrices and vectors. The mathematics of matrices and vectors is called linear algebra. Okay, so the mathematics of matrices and vectors is called linear algebra. So that means that in the later lectures of this course, we're going to spend some time and help you to understand what is linear algebra. So this is a very important thing for the development of this course. Linear algebra. Okay, so it is this is a fancy name, right? So, but it mainly talks about how to operate on matrices